In this lecture, we are going to discuss the topic of what's called retarded potentials. Essentially, what we're going to be doing is now looking at the time dependence of our electric and magnetic potentials. And so if we start with the Lorentz gauge, what we get is two equations. One for the electric potential and one for the magnetic potential. And for a description of the D'Alembertian, this operator, the square with a square symbol, you can refer to the previous lectures. Anyway, so we have these two second-order differential equations to solve, which are essentially wave equations. They're inhomogeneous second-order differential equations. And if we were to consider the static case, where, basically all of these are zero, then what you get is, you would get something like this. You would get the Laplacian for each equation, like so. Okay, and then the solution to that is, in this case, for the first one, for the electric potential, the well-known Coulomb's law. Where if I wanted to remind you what these symbols are, if we had some charge distribution, some infinitesimal volume of charge right here, then the distance to the point r prime, the distance from the origin, and then the distance to the point in space where we're measuring is r, and the difference between those is script r, like this. Okay, so we worked this out before. Now if we want to consider the non-static case, which is what we want to do, so we want to include time dependence, then we have to consider what is the time doing in the problem, because information about this charge cannot travel faster than the speed of light. So if I have some charge over here, Q, let's say, and that charge was, say, moving like this, and I'm over here measuring that charge, then I have to wait for information to get to me about the motion of that charge. And that information cannot travel faster than the speed of light. So if I think about it, I now have something which is called the retarded time of the time earlier is equal to the time now minus the travel time. So it's kind of like the problem that you have in astronomy, where the light that you see from a distant star, it left that star millions and millions of years ago, and it's just reaching you right now. So our time right now is t, the time at which the light left the star is t sub r, and the time it took to travel a distance from the star to me is this r divided by c. So what we can do now is then just modify our equations by adding in a time. So we have the electric potential measured at some position r at a time t, and it's equal to 1 over 4 pi epsilon naught, the integral of the charge distribution at a position r prime at a time t sub r divided by the distance and then integrated over the volume. So we could do the same thing with the magnetic potential. Measure the magnetic potential at a point r at a time t right now, and that's equal to mu 0 over 4 pi integrating over the current measured at some position r prime at some earlier time tr divided by the distance between those two things, the current and the observation, integrating over volume tau prime. Okay, so now what I want to do is to apply that second order differential equation to it. And so if I now want to measure, let's say, or I want to measure, if I want to calculate this quantity, then what I'm first gonna do is measure just the first derivative. So I'll take the gradient of the potential, which would be 1 over 4 pi epsilon naught. And using the chain rule, I get the gradient of the charge distribution over r plus the charge distribution, now the gradient of 1 over r, integrating over the total volume. Okay, so let's take a look at those pieces. So the gradient of the charge distribution is the derivative of the charge distribution times the gradient of the retarded time, which I can now rewrite as minus 1 over c rho dot the gradient of the distance r. Because if I look at this, essentially this drops out and I get minus 1 over c, the gradient of r. Okay, so this gradient of r I can write as r hat, which means that the gradient of 1 over r is minus r hat over r squared. Okay, so anyway, so these relationships can be worked out in problem 113. So if you go back and look in chapter 1 at problem number 13, we actually work out some of these things with the gradient of the distance r. Anyway, so if I put all the pieces together, then I get the gradient of v is 1 over 4 pi epsilon naught, the integral minus rho dot over c r hat over r minus rho r hat over r squared integrated over the volume, like so. Okay, so now let's apply the derivative again to give us the Laplacian of the potential, and that is the divergence of the gradient of v. Okay, so let's work that through, and what we get is 1 over 4 pi epsilon naught, the integral 1 over c r hat over r dot the gradient of rho dot plus rho dot times the divergence of r hat over r. Okay, so that's the first part. And then we have minus r hat over r squared dotted with the gradient of rho plus rho divergence of r hat over r squared. And then you integrate over the volume. So essentially, I've had to take that divergence through these two terms right up here. Okay. Okay, so let's take a look. So what is the gradient of r dot? That would be minus 1 over c r double dot, rho double dot, so the second derivative of rho, the gradient of r, which is equal to minus 1 over c rho double dot r hat. Okay. So let's take a look at the divergence of r hat over r. So that is 1 over r squared. And if you remember, the divergence of r hat over r squared is 4 pi times the Kronecker delta. Okay. So again, we went over a number of these relationships in chapter 1 of the book. Okay, so let's put it together now. What do we have? So we have the Laplacian of v is 1 over 4 pi epsilon naught, the integral 1 over c squared, rho double dot over r minus 4 pi rho, the Kronecker delta, integrated over the volume in the primed frame. Okay, and how did I get that? What happened to all the rows with one dot on them? They essentially cancel each other. So yeah, so anything with a rho dot canceled. So they fell out of the problem. So what we're left with is something like this, which we now can kind of summarize and say that the Laplacian of v is equal to 1 over c squared, the second derivative with respect to time, 1 over 4 pi epsilon naught, the integral of rho over r, integrating over the volume. So that's that first term. And then the second term has the delta in it, the delta function. And so when you integrate over that, it just gives you the function at that position r. So that means the second part is minus rho as a function of space and time divided by the permittivity. So essentially what I get is 1 over c squared times the second derivative of v with respect to time minus rho over epsilon naught. So if I subtract the time derivative from both sides, so what I've achieved is essentially this result back again by considering the equation in both a retarded time and now I get basically in the time of right now.